people who are viewing online confirm the quality of audio? Can you check maybe please in
Somebody can say chat live chat from through live chat they can
okay.
live chat is
Hello. Can you check and tell me whether it's coming okay? So how many of you attended the last Saturday session? Okay. So how many of you did not? Like just so that I know. 1, 2, just 2. Okay. So we'll start in a minute. We're just figuring out whether the audio quality is good enough for people who are viewing online. Okay. So one second. Okay. So the audio is good.
people have to
So can you?
they have to replace it.
Okay. Can you just confirm once?
They have to send the seat.
Okay. So people who are viewing online, can you just quickly? Okay. So thanks for confirming. We can go ahead then. Yeah. Okay. This is okay, Rangarao. You can leave. This is fine. Yeah. Okay. Thanks. Okay. So we can get started. So last time we were looking into attention and how that came into being from sequence to sequence tasks, and how we were using attention for building a new architecture altogether. So one second. So can we like I'm just going to do a little bit of a recap from last time, just so that everyone is on the same page. So we started building sequence to sequence models last time, where they were being used to, let's say, translate Hindi to English, a source language to a target language, and we used RNNs to encode the Hindi sequence, and then that was relayed to the English RNN, or the RNN that is used to decode English output. So we were calling the first sequence of RNNs as encoder, and similarly the sequence that actually decodes English output as decoder. This is just like naming, and we also realized that there is a big bottleneck here, because everything in the source sequence has to be encoded all the way towards the end, and that is the only connection from the encoder to the decoder. So everything about the Hindi sequence should be loaded in that vector so as to be used by the decoder to translate everything in English. And this is not ideal because, you know, if the sequence is long, this vector might not be able to encode everything. And secondly, this is the same, and this is like, let's say when you're predicting the word waved, ideally you want to look into, let's say, leheraya, or let's say similarly when you're predicting the word flag, you want to refer to jhanda, right? Like when you want to know what is being waved, and the answer is here, right? Jhanda. So, but this connection does not exist, at least in this model. Every information is relayed through this last state, which is again not ideal. So we introduced what is called as attention last time, to be able to use or attend to sequences dynamically, attend to tokens dynamically. And just to recap attention, we developed some intuition about it using key value queries, or like traditional dictionaries. So these are like hash maps or dictionaries that you learn in your data structures class. So we discussed this last time as well, where let's say if you have a word like Kinshuk, in a traditional dictionary, let's say this is your query, in a traditional dictionary, uh, okay, in a traditional dictionary, you will go and look at all the keys here, and this is a match, right? So Kinshuk matches with Kinshuk here, so we can say that the value of 419 is the final value. So let's say this is an useful application when you are trying to figure out where does Kinshuk sit if you're trying to look up in the room directory Kinshuk, right? So you have a query, you have a set of keys, you try to match your query with a set of keys, and if there is a match, you take that value corresponding to that key, and that becomes your final output. So if you want to know where Kinshuk sits, the final output is 419, which is the value corresponding to the key Kinshuk. So this is like, again, this is something you have done in the past in a, let's say, data structures class. So attention is very similar, but instead of a like exact match, it's a soft lookup. So let's say you have a word like Manish. Manish does not really match to, so this is your query now, it does not match to any of the keys, but it somewhat matches to, let's say, Danish. Let's say maybe this match is 0.88. It does not match at all with Yash, so let's say this match is 0.01 and so on. So this is a soft matching between a query and a set of keys, and based on the quantity of match or based on the strength of this match, you take the values in that weighted fashion. So let's say if it matches very strongly with, like, Manish and Danish are very close, so you take this value, you weight much higher than other values because this match is much stronger. Question? Yeah. Yes, yes. So in, like, when we develop transformers or when we talk about transformers, these are vectors. But if you were to think about this particular example of finding the office or the room directory, then this could also be like real values. It could be anything essentially. So you should think of this as V1, V2, V3, all the way till V6, right? This could be a real value, this could be a scalar, this could be a vector, anything. Ultimately, what you are doing is based on the match, you are doing a weighted sum. So ultimately, you will do something like Wi, Vi, weighted sum. This weight is determined by how strongly does your key match to the, how strongly does your query match to the key. Again, like, this is something you learned, it's a soft lookup. We can apply this now to an RNN. So let's say when you were, let's say you've already predicted the word minister, you want to predict the next word. So this hidden state after the RNN becomes your query vector, and these are all the keys that you want to ideally match. You want to look up what should I predict next, and you try to match with all the potential hidden states in the source sequence. And let's say you get some scores by matching, let's say, this with this, and so on. So you get like 4 scores based on, let's say, the quality of match between this token and, let's say, all of these tokens. And you want to predict what comes after minister, and you realize that this query matches very strongly with this word Leheraya. But these are unnormalized values, so a very standard practice is to take softmax just to exponentiate and normalize, and this gives you some vectors. These are called as attention vectors. We talked about them last time too. Right, so these sum to 1, and you can see that maybe this hidden representation has matched most strongly to this last token Leheraya. So what we will do is we will, in this same, so we will consider these as values, and in the same proportions that we just arrived at, we will take a weighted sum. So in the weighted sum, this will have a 0.76 weight, uh, because this was the strongest match. And using this weighted sum, you will make the prediction for what is the next word. So it turns out that the next word is waved because that is what the model had chosen to look at. Lehraya. Lehraya corresponds to waved in English, sorry. And you are, I think, now hopefully beginning to see how this mechanism lets you dynamically choose which portions of the source sequence you can attend to. Any questions? Yeah. This one? Okay. So everything clear about this? We discussed this last time also, but I thought I'll just give you a quick recap. Okay. So this is how attention was originally developed, designed, innovated around 2015 in this breakthrough paper called Learning to Jointly Align and Translate. So I showed you this example of how different languages might have a different order. Some orders might be like subject, object, verb, some might be subject, verb, object. So you need to align different words to be able to correctly do translation. So this attention mechanism is a way of aligning as well. You are deciding at runtime dynamically which words should you look at to produce which words, right? So this mechanism is called attention, and this has become very, very important because there are new architectures that are developed and designed solely based out of these architectures, or solely based out of this mechanism. Right, so if you were to just complete this picture, you will take like in this fashion the weighted sum of these, and that will be used to make the prediction. And if we just organically look at what was the attention after you have trained the model, so this is for predicting French from English source. So I had discussed last time too that let's say you are translating this word European, like the model has chosen to attend to this English word of European. Similarly, let's say 1992, the model has directly picked 1992. Whereas if you imagine in the older scheme of things, to correctly predict 1992, the model would have to relay this signal all the way from the encoder end state to the decoder first state, and it goes sequentially. Now it can attend to 1992 directly, and this is very, very useful because it can directly copy, let's say, dates and so on. Right, so this is the paper where this picture and the attention mechanism comes from. There are several ways to compute this match between the query and the key. One very simple is you take a dot product. So if the two vectors are similar, then dot product will give you a high similarity. So one simple fix to this is that scale of dot product can increase, because if you have larger dimensions, then the dot product increases. So one suggestion here is to just scale it by 1 upon root k. This is just a scaling factor, nothing really fancy about it. But you can really choose your own matching function, which is a function of query comma key. Okay. So you are also noticing that this need not even be symmetric. You can really choose your own functions here if you want. So now let's try to start from this and really tackle the problems that we faced with RNNs. So there were two problems with recurrence. One was it is sequential. Sequential is a problem because one, you need to really have the output at t minus 1 state to be able to process the time step t. So it has to go left to right one step at a time. That's not ideal again because you are stuck with processing one time step at a time. You cannot parallelize, you cannot speed up the training. And second, by virtue of left to right, like interactions between the two words depend upon how far they are. So if the word student and homework are very, very far, it will be very hard for the model to understand that we are talking about the homework of students, right? Because again, it has to go left to right and it's very sequential. Questions? Yeah.
So in the real-time translation, so do we use RNN or this text mechanism?
So right now, if you're using RNN, it will definitely involve attention. So attention is such a good idea that most RNN based architectures will have attention. But in 2025, very few people are using RNNs. So most of the industry has migrated to transformers because it is not sequential and therefore can be parallelized. So it is much easier to train on larger data sets. So if you can parallelize, you can like essentially process many sequences in a given amount of time. So I'll discuss how much speed ups can you expect and so on. But understanding attention from RNN is a good idea because it helps you understand how you are dynamically choosing what to attend. Any more questions? Yeah.
When you were saying sequentially, so d minus 1 and t are like related, so it is the strength is more kind of Markovian relation, but not the context length from 0 to 2, 3.
Yeah. Yeah.
So are there like caching techniques in here to maybe extend the context from one step to like at least be past? So future can't be maybe seen at t minus 1.
Yeah.
But you are saying ki this mechanism just is like one step at a time.
Yeah.
So have there been caching so that ki I have 0.
Yeah. Yeah. So the question is, in RNNs, like there is a Markovian sort of relation where you are looking at just the last hidden state. Are there ways to cache previous hidden states to be able to use that? So occasionally people will use skip connections where, let's say, maybe output of k minus 1 state is also an input. That is typically done at depth rather than at breadth, in the sense that when you have outputs of layer 1, they are typically fed to layer 5. These are called skip connections or highway connections. But that is not so often done in RNNs. The assumption or the hope is that the h t minus 1 that you are getting here, which is an input to the RNN at time step t, will hopefully this will hopefully communicate everything that is useful. Ideally it can, but practically it becomes hard.
It's kind of going average. So it's
Yeah, it's a complicated matrix multiplication. It's not necessarily an average, but average is one function it can learn. Yeah, if that is necessary.
What exactly the content of hidden state of transform?
So that's a good question. What exactly is the content of these hidden states? So these are real values or real vectors. It's very hard to interpret them. Like you cannot say that it has encoded color or it has encoded information about that word. There are experiments you can do to identify and extract, let's say, whether it knows about the tense of the sentence, or whether it knows whether it was written in active voice or passive voice. So that information is communicated, but it's not very interpretable. Like you can't look at the vector and tell the content.
So when we have that vector, can we do a vector lookup and then figure out what is that there?
Yeah. So you can potentially match it to other vectors and see that, okay, it matches to vectors of colors or vectors of objects or vectors of sentences that are written in past tense. But that is the only nature of evidence you have. You cannot it's not very cleanly interpretable as, let's say, a representation like bag of words, where you can say that, okay, this word is encoded because this index is 1.
But the output also is the same thing, right? The output also is also a list of is a vector that we believe is going to be whatever it is, right? So basically, whether it's hidden state or output state, all are represented in the same way.
Yeah.
Is there any other different representation?
Yeah. So even outputs are represented the same way, and the question is like, can we interpret them? The answer is again very hard to interpret. Even the outputs or the values
will be very, very hard to interpret, and which is why like a lot of people say that these are black box models, we don't know what they're doing, they're inscrutable, they're uninterpretable, they're unexplainable. So all those concerns stem from like this very nature that we don't know what is really encoded or how to really interpret a vector of numbers.
Is it, it can be any real value, it is between 0 and 1 only?
No, it can be any real value. Yeah. And it's also maybe like if you want to sympathize with these systems a little bit, like let's say if I were to record fMRI scans of your brain and look at the neural activity in your brain and give you graphs, you also won't be able to tell what you were thinking. Or if I gave you graphs of some other person, you will like, it's just neural activity. You will have some like voltage differences, very minute voltage differences that you can check, but again that becomes also very uninterpretable. Like you can't look at an fMRI scan and really tell what was going on. Yeah, for better or worse. Okay, so we will design a new architecture called transformers, which is solely based on attention, or rather self-attention, because all words look at each other. So unlike the previous setup where we had just one embedding for a word, here we have 3 embeddings for every word. One is this value, key and query. So the query of a particular word, which is a vector like an embedding, looks at the keys of all other words including itself, identifies a match, and that match is similar to the lookup match we were talking about. Once you normalize that, that becomes your attention vector. So based on, let's say, how this homework query matches with, let's say, the key of the students, you get a number like 9.2. Similarly, you get other numbers like 0.1, 2.1 and so on. You take a softmax, you convert it into probabilities like, let's say, 0.7 and so on. And then based on these attention values, you take the weighted average of all these values, and that becomes your output at step I. So we discussed this at length last time. So just to give you a little bit more formal backing or formal grounding. So if W1 to Wn is your sequence, so W, let's say 2 is homework, right? So now what you first do is you take that and pull out a row from your embedding matrix to get a vector. So now x2 is the, let's say, the vector for homework, right? And it is d-dimensional. It's a d-dimensional vector. Now you take this homework vector like xi, and you multiply it with 3 matrices: a query matrix, a key matrix, and a value matrix. These are all d cross d matrices, square matrices. And if your embedding is unique, if your vector is unique, you will get a unique key, unique value, unique query. That I believe is clear. And so similarly, you can get a query of vector, a query of homework, a key of homework, and a value of homework. And then you start matching these things. So EIJ means how strongly does the query of ith word or token matches with the jth token. And of course, you will also compute E of, let's say, I comma I. So the word can also look at itself. And once you have this, these are unnormalized values, you exponentiate them and normalize them. This is the softmax operation, all right? And yeah, now you basically take OI and do the weighted sum with values. So every word will have an output after we have done this self-attention operations. This is important to keep in mind. So you do some like look up at every other word in the sequence including yourself, you match to other keys. Based on that match, you do weighted averaging or weighted addition, and you get an output for every word. So if we were to go back to this particular slide here, where was this? Okay, here, right? So at the end of this operation, 1 second. At the end of this operation, like you will start with representations like x1, x2 and so on. These are vectors, but you will get O1, O2, O3 all the way till On. These are output vectors after performing, let's say, self attention. And now, so you can think of this as a block. Everything is an input to this, right? And you get an output. So this O2 will now be very, very contextual, because O2 is a weighted average of all the values, is a weighted sum of all the values based on the weight. So this word students, which was originally only representing students, now has information about, let's say, the fact that they are late, or the fact that they are late on homework, because of this dynamic attending to other sequences. So is this point clear, that now this representation O2 is highly contextual? So if this was a word like apple, by the context of it, it would have figured out that are we talking about the word fruit or are we talking about the company, because of the context. Yeah, question?
Confusing because so let's say all the vectors are some random numbers, and then you compute the similarity scores, and then attention after that. Then how do you tune them at all? In the sense that what is your ground truth?
Yeah. So we have not yet discussed how to train these systems, what is the loss function, how do we even end up with these vectors. But assuming we do that, and I'll come back to that towards the end of this lecture, how to train these systems. But assuming the word student has information about student, you are at least able to hopefully appreciate that the homework can access this information. So if these vectors were properly set, then the problem of contextualization is somewhat solved, or at least modeled here.
The O1, O2, O3 are the embedding vectors for those words.
Yes, so they are not, like these are d-dimensional vectors. Even though we are calling this like as the nth vector, it no longer, or it's not only a vector of homework, it has looked at everything. Right? Yeah, question?
So it has looked at everything, but we have just done the weighted average. So that averaging does not have the ordering. Like
Yes. So the question is, it does not have the ordering. Yes, I agree. It does not have the ordering. Yes. Anything else? Sorry, I cut you off.
Yeah, so is that it's having repercussions?
Yeah. So the question is, like, there is no ordering, which is true. Are there repercussions? Yes, there are some repercussions. We lose some performance, but we will add ordering information into the system very soon.
So here actually, as the words are increasing, this n is also increasing.
Yeah.
So that matrix size is also increasing. So is there a limit to the width?
Yeah, great question. So, so is there a limit? So one thing that you are maybe noticing here is that there are a lot of n cross n operations, right? Like everyone is looking at everything else. So the complexity of these systems are n square, which kind of initially limited a lot of progress on how many sequences can you encode, how many tokens can you encode. So that is called the context window. How much is the context window? Typically models will have a fixed context window, which is to say that they can only consume sequences of a certain length. So maybe models beginning from 2017-18 had a context window of 512. But if you now look at the current discussions, people are talking about, let's say, 1 million context windows, because they have been able to really do interesting innovations over this attention mechanism to really cut down on this complexity. I'll discuss a little bit of this in towards like a few more slides after this. Yeah.
Sir, is there a relation between the size of the context window and D?
Size of the context window and D, like is there a relationship between the size of the context window and D? Not necessarily, but if you have a bigger GPU, a larger compute budget, then you want to increase both. So if you look at architectures, they tend to be correlated. Higher context windows would mean that you need to encode a lot of information because there are a lot of words to look at. So you would typically also increase D if your compute budget allows. So nothing in principle says that they have to be correlated, but they tend to be correlated.
Because if I am multiplying the embeddings by Q, K and P matrices, and I have a lot of embeddings, the capacity of Q, K and P being D plus D matrices is kind of limited.
Yes. Yes. So yes, that's right. If your D is too small, then you are limiting the capacity. Yeah, for sure. Like imagine a 2 cross 2 dimension, like that is very, very limiting. Yes. Any more questions? Okay. So I also discussed a little bit of this last time in the matrix form. So the beauty of some of these operations is that so the beauty of a lot of this is that it can be represented in matrix form. So like we discussed this, and this was supposedly your homework to kind of like really feel comfortable with this, but this can be done in matrix form, and like on GPUs, matrix multiplication is about as fast as like almost vector to vector multiplication. So you are like almost able to go from embeddings like this X to outputs in like no time. Like it's like almost one big set of matrix multiplication operations. So it happens really, really fast. And that is like one very important property of transformers. It happens like it is able to like parallelly like process everything. While the word homework is looking at everything else, the word student is looking at other words. It is like amazingly parallel. So like when you're doing matrix multiplication, let's say this row is to be multiplied with this. This can parallelly happen from this row and this row, right? So matrix multiplications are very efficiently implemented and they are very, very fast. Question?
So how can you actually do it in parallel? Because the fact that the homework actually changed the vectors of other words during the process of homework.
Right. Good question. So how can we do this parallelly? So what happens is that at like let's say when you begin, you fix your embeddings and you do this business of matching queries with keys and taking the weighted dot product and everything. Nothing changes then. Once you get O1 or OIs outputs, then they become your next embeddings and you do this operation one more time. You do this operation one more time. So you can stack these operations, but during like in one layer nothing changes. In one layer you are not changing the vectors of students and homework. So maybe like here, like if you look at this page, right? So let's say you had a vector of students, like x2 was a vector of let's say students. Similarly, q2 was a vector of students. You are not changing them. Like nothing is being changed in this forward pass anyway. Like this is like your output of let's say output 12 of homework is determined by, let's say, Q2, Q, Key2, V2 and all of that, but that there is a relationship between them, but there is no like, it's not like they're changed during the computation.
So you will do all this and then store it somewhere and then like accumulate it all in the end. So you, because all of them are happening parallel, sometimes you have to consolidate.
Yeah. So basically, like one, yeah, that's a good question. So something like one thing could be like you need not like these are like for instance, you can imagine that matrix multiplications happen parallelly, right? Like let's say you can treat that as a level of abstraction here and say that okay, this and this multiplication can happen parallelly, and internally CUDA does that for me and will do the synchronization and everything. So it's not like if the first row and the second column was computed first, we will have to maybe do some weighting and some amount of synchronization, but all of that is taken care for you. Okay. So something to like think about here is that it's no longer sequential, it can be parallelized. Interactions between two words are not contingent on how far they are now. So these are like good properties to have. So there are a few issues with self-attention. So one might say that it's just a weighted average, right? It's a weighted average of all values. But we know from deep learning that non-linearities are super useful. Otherwise, we'll end up learning just linear functions which are not very expressive. So one very simple solution to this is that, let's say you have these words, you apply self-attention, you get O1, O2, O3, On. This is the self-attention block that I was talking about. You apply a feed-forward network here, which is a fully connected neural network. And let's say if this is d-dimensionals, you get d-dimensionals out. This is the neural network that I was showing you in module 2 and module 3, just like a regular feed-forward neural network. And now there is a lot of non-linearity here because of the neural network. And now this d-dimensional output will become a part of another computation like we did in the first stage. So just like when we were stacking RNNs or we were stacking neural networks, you can stack these attention blocks. So once you have O1 here, O2 here, this can be your input to another layer of self-attention. Say that again. Thanks. Why do we need to stack? For the same reason why we need deeper neural networks. They capture higher order bits, they can capture more abstraction. That's right. But it is like before a feed-forward network, it's a linear combination. After that, it's a non-linear combination, but it is only capturing, like let's say, somewhat superficial features. Now, if you want to compose those superficial features into more complicated features, then you need to add one more layer. So think of the vision example, like maybe the initial layers capture simple things like lines, but if you need eyes, you have to combine multiple lines in a particular shape. So like, yeah, that is always the reason to justify depth in deep learning.
Does the neural networks for each OI, are they separate from each other? Are they independent?
So for each OI, are they separate or independent? Is that the question?
Yes.
So basically this OI was computed using the formula that we just saw. So it is looking at all these words.
No, the feed-forward network.
Okay, great. Yes. So this OI is passed into this feed-forward network to give you another vector. This feed-forward network and this feed-forward network, they share weights. So they are connected, but like they share weights. That's the only connection. Not necessary. So basically you need so when you are starting from here and like to go from here to here, you need this output, right? So you need some synchronization, but like you don't have to, yeah, you have to essentially like you have to do this sequentially. Like the depth part, you have to do this sequentially. To process layer 2 outputs, you need layer 1 outputs. So
There isn't any theoretical proof on why we need the second layer, how many layers do we need?
yeah.
Black box
So great question. So like in feed forward network, there are some theoretical results that show even an infinite like a 2-layered network of infinite dimensions can encode many functions. But in practice, the optimization of it is very hard. Like you rarely can learn complicated things with a two-layer network. So in theory, you can do that, but in practice, it's very challenging. Yeah.
So let's say I didn't get the accuracy. Okay, dump one more layer.
Yeah. So far the trends we have is like more data. To be able to use more data, we need a bigger network, which makes sense, right? Because you are running out of capacity, and if you can consume bigger data with a bigger network, that happens to be much better than a smaller network with smaller data. That's like very clear at this point of time. Like there are scaling laws, so not like a linear curve, but yeah, it's like GPT-3 versus GPT-2. The only difference, for instance, is the size of the network and the size of the data set. Actually, I will go towards the end of this class, I will give you all the values for GPT-1, GPT-2, GPT-3, just so that to ground this architecture on like how much scaled up that is. Okay.
This feed forwards is said as sharing weights.
Yes.
So we have to define number of feed forwards at a layer.
Yeah.
Then our context window is very much fixed.
Yes. So the question is like, since we are having a number of feed forward networks, we need to know that number ahead of time. So the n is typically fixed for a network. So maybe this is an important point. So n is pre-decided ahead of time. So you might ask me what happens if your sequence is much shorter than n. I'll come to that question. Yeah.
One other thing, like initially the first one is just the weighted average of the values. So like values sit in a vector field.
Yes.
And this weighted average will take me in the same vector field. But when I do this non-linearity, am I guaranteed to be in that vector field, or I will?
No, you can transform to a different dimension also if you want. No longer the same field. Yeah.
So then the self-attention at each stack, are they different modules? Like
Yes. So the weights of this self-attention and this self-attention are not the same. Yeah. Okay. Great.
What could be about like define the depth of the feed this FF?
So this is
Depth.
say that again.
Number of neurons in a per layer and number of layers in this FF.
Yeah, so this FF is generally a 2-layered network, but this is also a hyperparameter that you can control. Yeah, but this block essentially will repeat. So if I were to make a block here, right? Okay, let me make a block with a green color. This block will repeat multiple times. So to understand this architecture a little bit more, this is like a very abstracted out version of this. So you begin with inputs, you get so forget about this for 1 second. Okay, I think I deleted that bit. Okay, sure. So let me cover that a little bit here. So one other concern with the model is that there is no positional information encoded, right? We don't know what is a third word versus what is a fourth word versus what is a 10th word, right? So one very simple, almost dumb idea is that we will add these positional embeddings. So you will have, just like you have x1 all the way till xn, you will have p1 all the way till pn. Just like xi was a r dimensional vector, pi is also an r dimensional vector. So p, let's say pi loosely encodes what it means to be in position I, right? So if the first word should have some special properties or should have some uniqueness because it's the first word, or second word should have some unique properties because it's the second word. Similarly, I word could have some unique properties just because it's an ith word. You define a vector, you define a vector pi which encodes what it means to be in position I. So one very simple solution that works to some degree is that before you even multiply this with the query key value matrix, you perform this operation xi plus pi. Okay, so your initial embedding of the word student will be slightly different if it is in the second position versus the 10th position, because you are adding, like let's say to x2 bar, you are adding x2 plus p2. p2 is also a vector that is random to begin with but will be trained as a part of the network. Just one second. Again, this may not be very intuitive. What is the role of p's? But think about it in this way, like every time I see the first word, I am adding a fixed value to it, a fixed vector p1. Similarly, every time I see the 10th word, I am adding the same vector to it. So if 10th word has a very unique need or a unique function, that information will be encoded in p10, loosely speaking. At least you can see that because the word student occurred in the second position, it will now have a slightly different vector compared to the word student occurring in the 10th position, because in the 10th position I am adding p10, whereas in the second position I am adding p2. So because of this, I have also created this unique like this distinction between student at position 2 versus student at position 10. And once I have this updated x, it is business as usual. Like you can think of another step here where xi is equal to xi plus pi. You can think of this as this, and then you just continue. So I've just added initially these positional embeddings. There has been a lot of research on positional embeddings themselves. Like there are some nice formalizations of like how positional embeddings could be sinusoidal in nature and so on. I won't get into the details of any of them, but a very simple way to represent positions is just through this addition of a new vector that is learnable in itself. And that's it. Like that's just one very rudimentary way of encoding position. So now if we come to this diagram, you start with inputs, you get x1 all the way till xn, you add position embeddings, so you add p1 to pn, then you multiply with k, q, d, so you get a qi, ki, vi, you do self attention. Forget for now what is masked self attention. It is for you, let's say, self attention. Then you do feed forward network and you do this n times cross n. So this in PyTorch code will look like loops. You are taking the output and you will consume that output and so on. So repeat for number of encoder blocks. So if you have n encoder blocks, you will repeat this, and now this will give you a d-dimensional output. But let's say you are using this to predict vocabulary tokens, then you need to project it back into a vocabulary space, take a softmax to give you probabilities, which is again like this component. This part should feel very, very familiar because you apply this everywhere. This part is common for RNNs also. You have to ultimately project it to the space you want and take a softmax. So basically, compared to an RNN, the new part is positional embeddings, like position is encoded in this fashion. You then take K, Q, V, 3 vectors, do self attention, feed forward, and you do this n times. This is equivalent of like blocks, like this is equivalent of depth in a feed forward network. Question, yes?
Can we, given that the positional embeddings are learnable, can we say that the magnitude of these positional embeddings kind of gives us a sense of how ordered the language is?
So the question is, can the magnitude of positional embeddings give me a sense of how ordered the language is? Good question. It may. I don't know the answer to it. It may very well happen that if the language does not care about the position, let's say you've designed a language like that, then there might be very similar position embeddings, or they might look very random. So there might be ways to discern the properties of language by looking at positional embeddings. I doubt people have looked into it, but it's, at least I don't know.
Would it be easy in the position embedding to a indexing from 0 to whatever the n value? Indexing instead of going with the vector representation?
Yeah. So if you want, you can think of this as a one-dimensional vector, like that is the same thing. But this is just d dimension, so we are doing that d times. So this is more power to positions. I mean, I'm not claiming that this is the best way to add position. This is a very roundabout or a very deep learning-ish way of adding position. Yeah.
Again, this is also a vector only, right?
Yeah, this is a vector, yes.
So these probabilities, like we will have the D output, D probabilities. So now these D probabilities actually will represent the vocabulary part of that. That is much more huge than D, right?
Yeah, correct. So this D is typically, let's say, 1000, vocabulary is, let's say, 50,000. So you will have this linear function here. Maybe let me. This will be like very, very, it will be D cross V. So it will take D dimensions to V dimensions. Yeah.
The probabilities will be then D dimension.
Then V dimensions, yes.
Why are we not calculating the probabilities after each loop itself? We feel that we got the answer. Why simply waste 2 more?
Okay. So you're saying the question is, why are we not computing probabilities somewhere in the middle rather than waiting till the end? So we decide generally ahead of time how much capacity we typically need. So if we think that we can hold 8 layers, the general practice is like, let's not dynamically select layers based on the input, because so there are good reasons for it. One is, like, if you want some sequences to consume all 8 layers, then for them second layer will have a very different role than a sequence where you just need 2 layers. So the idea is, like, like generally how many layers to have is determined by how much compute you are willing to spend. Yeah.
Whether you got the answer in the second layer or you didn't get, or you get the
Yeah.
but you just got passed.
Yeah. So it can happen that for many of the sequences you don't necessarily need all the layers. You could have extracted out the answer from 4th or 7th or 8th layer rather than all 12 layers. But you choose the layers that maybe like you decide the number of layers based on like how complex the task is and how much budget you have. Like you can potentially do that if you are like, so people do that, let's say in distillation. Let's say Gemma 327 billion was trained from a much larger model. So these ideas are useful when you're doing distillation, but people don't dynamically like take out elements of a model and use that. So distillation is like essentially that.
Where we don't decide the end, but sort of during the training process, we figure out how quickly we get to the answer and then drop the end
So,
on the
okay.
tracker.
So you will decide n for every example or for the data set?
Every data set.
Okay, let's say you decided that for every example, but at test time, how will you manage that? At test time, you don't know the answer. So how will you decide how many layers to use? So generally, that's why I think it's fixed. So you can maybe say that, okay, if the model is confident after layer 4, let's just run it till layer 4. But that's just not how it is done though. Yeah. So generally, like the idea is like we'll have the same computation, like the model is fixed for all sequences. So that, yeah, it's just like one less thing to worry about in some sense.
These positional embeddings, we are just adding like xi plus pi.
Yeah.
So any of these matrix multiplication would be again like q into xi would be now this.
Q into xi plus pi essentially, yes.
So instead of thinking it like xi plus pi, I could also think like qi plus some q bar, and then xi is same. So internally, this positional embedding could have been always in this kind of learning. And
Yeah.
just enforcing this explicitly.
Yes. So you're enforcing this explicitly. Some amount of positional information is also learnt by that. So the fact that the always comes in the first position, models can learn that. And like in typically, like I'll touch upon this a little bit later, but when you're doing language modeling, you will not have the entire sequence with you. So you will go left to right and you will generate sequences, right? So let's say if I ask ChatGPT a question, give me a poem about IISc, it will start to generate the poem. So let's say like the first word it says is IISc. Now when it has the second word, it only has IISc and the prompt to look into, right? It does not have the future to look into, right? For the next token, it will have IISc plus the first predicted word. So when you're doing decoding, when you're doing language modeling, your context is variable length. So just because you're attending to a variable length sequence, that itself will give you position. That itself will be enough to tell you what is the order. Like you can extract out position from it. So in some sense, like the positions, like if I were to just let's say forget, if I were to just say like forget about this, we don't care, like ignore, then this means you lose like 2 to 3% accuracy, like not a huge deal. If the task really requires position, maybe you lose 5%, but that's the kind of like it's a small thing. Okay.
So
Q internally can have this.
plus some q naught.
Yeah, but the other part is also qi will depend upon the word I. So maybe we can discuss this in more detail towards the end, like one-on-one. Yeah.
All this from input to the probabilities we are doing to predict the just next one word.
Yeah. So how will we, like, how to adapt this to a task? We have not gotten there, but you are already, I think, beginning to see that these probabilities can be used to solve some tasks. Yeah, we will come to that. Yeah. Any more questions? Okay, what happened to this? Oh no. Okay, perfect. Yeah. Okay, so if we so this is like the basic self-attention block. So if we have to fully understand this paper of Attention is All You Need by Vaswani et al. It is self-attention blocks plus these residual connections. These residual connections are these skip connections. And there is this interesting new concept about multi-headed attention. So I'll tell you a little bit about this, but transformer model is mostly what I showed you in the last slide. So this paper, Attention is All You Need, is basically that. Attention is All You Need is also single-handedly responsible for thousands of papers that have title All You Need, like memory is all you need, or X is all you need, or vision is all you need. Like if you go on Google Scholar and search for this 4-gram is all you need, you will find at least 1,000 papers. So these are the people who are to be blamed for this. Okay. So, but you are also visualizing that why they chose this title, Attention is All You Need, because they have taken away recurrence, and the only mechanism by which the words interact with each other is through attention, which is why the title is Attention is All You Need.
But this is basically borrowed from the 2015 paper.
The concept of attention is borrowed from the 2015 paper, which applied attention on recurrent neural networks. Yeah. So there is, in fact, like if you're interested, the first author here, like this person, Dimitri Bhadeno, he has also shared his story about how he came to discover attention. So you can look it up. So that's like a little bit of a historical anecdote. So let's talk a little bit about multi-headed attention. Again, like I could have ignored this also, but it's easy enough, so I thought I'll cover it. So instead of doing KQV, you can think of this 4 times or 8 times or 10 times, where each of these operations are done in parallel and are independent of each other. So instead of doing this once, you can think of these as doing them 4 times, 8 times, 20 times. So it's called multi-headed attention. The way it works is like you do this, let's say you have the KQV for head 1, similarly you have KQV for head 4, and if you have a sequence of n dimensions, right? So you get basically n cross d from the head 4th, n cross d for head 1. If there are 4 heads, you basically get n cross 4d output, right? And then you take it back to d dimension and then apply this again. So instead, like this is like the idea is very, very simple. Like instead of just doing this once, you do this parallelly 4 times, 8 times, 20 times, whatever times you want, and you compute these separately and then club them together.
So basically break down into that 4, what are 4 equal parts?
4 parts equal, like you can, so these are different weights. Head 2 has different weights, different query, different keys, different values. So one motivation for why this might be interesting is there is a lot about student that is interesting. So it's like multi-dimensional, and maybe one head is deciding to look at student in context of homework. Another head is looking at student in context of being late. So different heads can look at different things. I will show you after you've trained a model what do different heads look at. But this is just one way of both increasing capacity and adding this modeling advantage. Question, yeah?
So when you're doing that step of calculating Q,
KV, yeah.
right, so at that point, even if you do it 4 times, how will the value be different for each one of them?
Because the weights are different. The Q, K, V.
That means you're saying that during the training process, when you come to that,
Yes.
each of them will
Because each will start with a different value, the gradients will be different. So they will converge to different values.
But how will the correlation between, let's take meaning of head 1 and head 2? There should be connection between each of them to make a meaningful.
Yeah, so they get combined here. That's the only connection.
Suppose, for example, I have, let's take 4 sentences, head 1 is taking 1 sentence and
No. This is not how it works. So entirety of the sentence is consumed by head 1. Entirety of the sentence is consumed by head 2 in parallel. So think of these as 4 different networks operating independently with different weights. You just club the output and then do it again.
same set of sequence is being taken by head 1, head 2,
Yes, exactly. They are computed parallelly, yes. With different weights, exactly. So think of this as 4 different networks that are trying to learn different things. Because learning the same thing is not useful. Like often it happens that there is quite a bit of redundancy. But if your model requires that different heads be differentiated, they learn different things, then that is possible.
But head 1, in the attention mechanism, head 1 learns something about whole sentences.
Yes.
The same with the different weights in head 2 will learn
This is
the same
might learn different things about the same sentence.
might learn.
Yeah. So let me actually show you what does it look at. So there's this paper called "What Does BERT Look At? An Analysis of BERT's Attention." You don't know what BERT is right now. Like, bear with me. I will introduce it and cover it in great detail. But think of this as BERT is just another transformer trained in some way. So if I look at layer 1, head 1, okay, so it attends broadly, it attends to every word in some fashion. Head 3 in layer 1 always attends to the next token. Attending to the next token is useful. Attending to the previous token is also useful. Head 8 in layer 7 attends to the separation token. Separation tokens are generally dedicated tokens. They tend to look at everything, and everyone looks at everything anyway, but they tend to store information at a sentence level essentially. So this head attends to periods. So different heads can attend to different things about in the same sequence. So different heads can potentially take differentiated roles. Sometimes they might be very uninterpretable. These are like definitely cherry picked heads and layers where they could make sense of what is going on.
How do we train different and like ensure that they have different weights?
Yeah. So we have not gotten into how to do the training. So let me take you there. So one thing to think about is, like, let's say when I start with something even as simple as a vector of d dimensional multiplied with another weight of also, let's say, d dimensions. How do I know that the first weight and the third weight will be different? Because the initial values are different, so the loss corresponding to this will be different, updates will be different, and what they converge to will be different, right? We have randomly initialized. If all of them are initialized to the same value, then all of them will take the same outputs, because the derivative will be the same.
But this is not the case in case of BERT.
Yeah, it's not the case in this architecture because this is different from this. In fact, the second row in this is different from this. Element 2 cross 2 comma 2 is different from 2 comma 1. All are randomly selected. That randomness is very, very important.
No, but in case of birth, this is not the case that they are randomly initializing them. Or is it?
So they are randomly initialized, yes. They are randomly initialized using some like ranges. In fact, like it cannot be like 70,000 value. Like there are some checks and balances, and there are like some good distributions to use to initialize, which is like outside the scope of this class. But like for purposes of this class, you should think that they are randomly initialized.
What are the criteria to decide what are good distributions to initialize? Very briefly.
Yeah, so like you ideally want values to be similar. So one criteria is you want to capture them within a range. And there are some papers which like people use the most common distributions that come to their mind. So like normal distribution is used very routinely for such initializations. Yeah. Even uniform is used very routinely for such initializations. Yeah, so really like something simple. I don't think there's a huge science around it. Okay. Cool. So assuming that you agree with how multi-headed attention works, this is just a different way of looking at it. So they basically are inputs to 4 or 5 or 10 different heads, and these things happen in parallel. Right. So this is essentially the transformer model. This is the diagram from this paper itself. So now let me talk more specifically about how you will use this for tasks. Like let's say if you were to use transformers for the task of machine translation, how will you do that? So just like you had an encoder and a decoder, you will have a transformer that's an encoder and another transformer that's a decoder, right? So here this is, let's say you are doing let's say Hindi to English. So this is your inputs, Hindi inputs. You do multi-headed attention, you do some sort of normalization and so on, like ignore this for now. And you have these, why are there 3 of these here? Because of KQV, right? Now the decoder, so let's imagine that we have the same scenario. Minister ne jhanda lehraya, and we have the English version of, so far, minister waved and we are predicting the next word. So let's say you have these, what will happen? You will encode these outputs also using a transformer. Do the first set of attention amongst itself in the English only sequence. So this attention head, the first one towards the right, is on English only, whereas the second attention head will use the keys and the values from the encoder. So just one second. So here, like the first attention block is just looking at the English sequence that you have already translated, but it needs to figure out what is the next word to output. So the query of this at this stage will go and look at the keys and values of the encoder. This is the same thing as the RNN, where we had the query of the decoder look at the keys of the encoder, right? So this was the lookup. So this was the very first slide of today's lecture. So you have an encoder transformer and a decoder transformer. The decoder transformer has this cross attention where it is looking at the encoded input sequences in Hindi because it has to translate Hindi into English.
What is that output emitting input pattern to the decoder? I mean, it's a general.
So this one, you mean? Okay. So the question is, what is this? So when you have, let's say, translated minister waved a, you need to feed that also in the decoder, right? So similar to the RNN case, similar to the very first slide we talked about in this class, right? You have to feed to these, like you have to feed minister here, right, to the decoder RNN. Very similarly, you have to feed the outputs that you have produced so far to the decoder. Question, yeah?
KV is the thing that they call as KV cache, is the same KV that
Exactly, yes.
what is K and V here exactly?
K is the key value, K is the key matrix, V is the value matrix. So when we're talking about this particular attention head, that is the K we are referring to. So I think like maybe the only point I'm trying to drive on this slide is that just like in RNNs, if you are going to do sequence to sequence modeling, you need to have two blocks, one as an encoder, one as a decoder, and the decoder will look at your encoder through cross attention here. So the encoder only looks at its own input because it's only encoding, but the decoder needs to reference Hindi words to be able to do the decoding, right? So this cross attention happens here essentially. This is like the cross attention.
Where exactly we are storing those outputs, digital wave return, because we are giving that as the input to the decoder, right?
Yeah. So whatever outputs you will get, you will pass that as an input.
Will be stored at some place.
Yeah, everything will be stored somewhere, right? Yeah. Like what is special about those? Like I'm curious why you're worried about storage there.
Because here in the encoder we pass that K and Q, right?
Yeah, so for inputs you already have the Hindi sequence with you.
Yes.
You can,
Let's take the first word itself. So Hindi, I'm not sure what is that word.
like minister, like right, mantri, yeah.
So then that K and V has gone into that decoder part. So what should I be passing this output emitting for the first word of that Hindi to?
Okay, so first of all, the entire Hindi sequence can be processed parallelly. You have the Hindi sequence with you. So all of this can happen parallelly. You get all the O's, Q's, values, everything parallelly in Hindi. Now you don't know what the output of the English sequence will be. So the very first token will be a start token, which is a hint to the model that you need to start generating. You will produce the first word looking at mantri. Hopefully your prediction is correct and you say minister. Now minister is your input to this system. Now minister will look at all the words in Hindi and figure out the next word should be ne. Like that is something I need to attend to, or maybe it needs to attend to other words like waved. So it might say minister waved.
I mean, basically it's training happens and we have then come to that part.
Yes. So yeah. So basically, like this is called. So this is like the training mechanism of transformers. I'm showing you training for, let's say, sequence to sequence models. That happens to be a little bit more complex than, let's say, just single sequence tasks. Question?
How do you synchronize K, V, and Q in this cross attention? Like, when we have cross language, so like key and value for that position can be for minister, and that in the other language it can be flag or something.
Yeah, good question. So the question is like, do these keys, queries, values collide with each other, and like they so in some sense they are operating in a different space. Like even though it's a d-dimensional space, they're different vectors.
Yeah, earlier we are maintaining like thing I is k, q and v for I like are synchronized all three, but here when we have
They're synchronized here also, right? Like because of this, like if you look at this portion here in green, in yellow, let's say.
here, but cross attention.
In cross attention, yes. So yeah, the query has to look at the key of Hindi.
Yeah, and same indexes. So like
Same indexes, yes.
monthly में झंडा लहराया. So if I index it first, monthly में झंडा लहराया. In English, query vector should also be like monthly flag and wave, not monthly wave flag.
Why?
Second index is query, that is waved query in English, and second index is jhanda value and key in Hindi. They will collect.
So here the index part does not matter, right? Like where did you, like you are looking at the waved query, it is being matched to the keys of Hindi to compute attention scores, which will then be used to compute outputs of Hindi, which so this is like whole sentence in Hindi is available, yes.
It is available, it has already encoded all the words, right?
Yes.
And then it can, the English encoder can actually word by word actually find that.
Yes, exactly.
Like Q is multiplied with all the K's to get that attention.
Q is multiplied with all the K's, yes.
Yeah, so that's how we get that the Hindi context K values and
Yeah. So one, maybe like I think a lot of people feel like this is a bit confusing. So one thing I can suggest here is that you go check out the transformers library. Hugging Face has a very good implementation of transformers. It is very, very simple. There is just there is a very clear attention block which takes keys, queries and values. But in cross attention, those keys and values come from the encoder rather than the decoder, even when you are doing the decoding. That's the only difference in code, essentially.
Earlier we had the key and the value is they do the what is the attention score to figure out which is the correct key for the current word that we are currently have to generate.
Yes, can you repeat that?
Is based on what is the next word that you need to generate. Is it or is all the words that are already generated previously?
It's based on all the words that are previously generated. So
That is where the confusion is. Then the K and B are for the words that are already generated or for the new word that is going to get generated that gets looked up, which is the closest attention score for that new word that gets generated that needs to be generated for.
right. So so maybe like let me explain this a little bit more. So let's like forget about cross attention for now. Let's look at decoder only systems. Okay. So these are the systems that are just doing decoding. So think of this as think language modeling. So just one example, GPT is a decoder, GPT is a decoder only model. GPT stands for Generative Pre-trained Transformer. So you just have one transformer block. So unlike the previous one, you just have the second component of it. let me see if I can copy this. Okay, so let's say you have inputs. So what is the task? You will have some inputs like x1, x2, x3, and you have to predict the next one, right? So let's say you have 3 inputs so far and you want to predict the 4th output, right? You want to guess which is the next word. You have, let's say, stuck badly in, you want to predict traffic, okay? And now what, but again remember that for transformers n is pre-decided. So let's say we are working with an n of 1024 dimensions, okay? So the way this will actually go in the model it will go as badly stuck in mask all the way till end of mask, right? Because I don't know what is the future here. I have to in fact predict the future. I have to predict what word can come next. This is the task of language modeling. This is the task of decoding. So of course this decoding could also rely and condition on Hindi input, but let's forget that. This is, let's say, just the task of English language modeling. Now what will happen here is I will do cross attention of everything. So even mask 7 will have a cross attention, but it is masked. That's why it's called masked attention. I had erased that word previously. Let me explain that concept a little bit. So when you are doing the first word, when you're computing attention, you multiply it with Q1, K1, Q1, K2, Q1, K3. But here there is only 3 words, right? So you set this to negative infinity, negative infinity, negative infinity. Why do you need to do that? Because after you do softmax, that value will just vanish. Similarly, Q2, K1, Q2, K2, and so on. So these are all infinity because the second query cannot attend to the 4th word that does not exist right now. Okay, and ultimately you will do those matrix operations that I had explained in the slide, and corresponding to the last, very last O3 after doing multiple rounds of encoder, you will ultimately get O1, O2, O3, O4, O5, O6 are completely useless because they don't mean much. They are all, because of this negative infinity, masked out. You will use O3's representation to predict the next word, right? And whatever that next word is, you will include that in your input and do this again. So the decoder is still like auto-regressive in the sense that it goes like it will generate a token, and then that token will be consumed, right? Got it? So just to give you some results of this particular architecture, this is the same Vaswani et al. Architecture, the same diagram. So this is 2017. There were 8 heads. Your D was 64. There were only 6 layers. So this is n cross n is equal to 6. It was trained in NVIDIA P100. Like if you want to draw car comparisons, this is like i10. It's not a very fancy car, very simple GPU. uh, quite cheap at this point of time. It took 12 hours to train the base model, and it took 3.5 days to train the larger one. There is a larger model also which has a slightly bigger H, bigger D, bigger N. And these were the results. So blue is a metric where higher is better for translation. Their numbers are not very much different, like some numbers are different, like 41.8 is better than 41, 28.4 is better than 26. But the interesting thing here is that it all can be parallelized. The encoder is completely parallel, right? So if you look at the training cost here, lower is better. So this value has been reduced almost by 2 orders of magnitude. Which is like, again, like these are all RNN based architectures or convolutional based architectures. The biggest difference is that it can be parallelized. Similarly, for like document generation, like perplexities are better, but like the biggest advantage is like here the perplexity is better, but the biggest advantage is time. You can actually train a lot more in the same compute budget, which is why people thought that why only use transformers for just translation or document generation? Can I train it on the entirety of my internet data? Which is what gave rise to pre-training. Earlier the idea or the concept was that we will only train the words. So words will be pre-trained by word2vec or glove or other mechanisms, and everything else will be not pre-trained and will be decided based on the task itself. But starting 2018 onwards, given this architecture, people thought that we can actually pre-train everything, and later if we have to change the architecture a little bit to meet the demands of the task, we can adjust it a little bit. That process was called fine-tuning. So pre-training plus fine-tuning became a paradigm. So you start with a model that's pre-trained. It is trained on lots and lots of data on the internet. So to give you an example of how BERT was trained, right? So BERT is just a bidirectional encoder, right? So why bidirectional? Because every word can attend to every other word. It can attend to even future words. It can attend to even words on the right. So the task that BERT paper decided was, what they're going to do is they're going to take a sentence like I went to the store. They're going to mask out these words like these, and they're trying to guess what the words are. This is very much like the fill in the blank tasks that a lot of us grew up on, right? This is our like English exams from class 5, class 10 and so on. The goal of the encoder, so this will be represented as mask, which means the model does not know what this is. The output at 2, output at 5 will be projected to predict went and store. The loss here in this example will be negative of log probability of predicting went at time step 2 plus negative of log probability of predicting store at time step 5, right? This is called the masked language modeling objective. And right, so BERT is bidirectional encoder representations from transformers. They said that we will randomly choose 15% of the words. Of those 15%, we will replace the input with this word, with this mask token. And to add some regularization effects, we will randomly change the word 10% of the times, and 10% of the times we will keep it unchanged. But the goal is to predict the word that was actually there in the text. So if the word was Kohli scored 100, they will mask out the word like scored, and the goal is to predict scored. This was the chosen task of choice to use transformers for, and this was trained in 2018 on books and English Wikipedia. So this is 2500 million, so you can think of this as 2.5 billion tokens or words, right, total. So remember these things. So BERT base was 12 layers, this is your D768, 12 attention heads, 110 million free parameters. BERT large was twice the number of layers, much larger D, 16 heads, 330 million parameters. Trained on this data, right? It was trained for 4 days on 64 TPU chips back then. Right now people have optimized it, and there are like some very nice, like the compute has also gotten better. Now you can train it within 1 day on a very simple, this is almost like a gaming hardware. You can do this in 1 day. After you have pre-trained BERT, you let's say have your own task in your own company. Let's say you want to predict whether this is a good trade idea or whether the financial sentiment here is negative, positive. You can change the weights slightly to meet the requirements of your task. That paradigm is called fine tuning. You can like typically done on few thousands of examples, but this is done on like billions of words. Yeah, right now if you were to train BERT again, it will take a day on 4 GPUs. This will take maybe like 15 to 30 minutes. Like this is very easy. This is what people do, for instance, if they want to use BERT. Those are all the random things we started with, which we didn't know the value to, which I told will get updated as a part of the training. Those are all free parameters.
You said that fine tuning, basically we are just putting some hyperparameter changing those values.
No, fine tuning is not tuning the hyperparameters. It is tuning the parameters itself, changing the network, but you already have a good set of weights because of this pre-training, and you don't want to move too much, so you only run this for a few thousand examples, and the model is good enough to give you a high performance on this task. Yeah.
How it is different from the transfer learning?
This is called transfer learning. You pre-train a network on a lot of data, and it works on, let's say, your task with some examples, on somebody else's tasks with some other examples, but the knowledge gained from all this process is transferring to your task, their task, and so on.
How many layers does this then changes, and which layers does this, because it's...
So it changes everything in the network, but very slightly, because you are not updating much, you are only updating for 1000 sentences. So you're doing very few gradient updates essentially. Yeah.
Why did BERT did not take up as this?
So BERT was quite famous within the NLP community in 2018. A lot of people started using it right away. It was not like, it was still a research project. It got implemented and integrated into Google search in 2019, 2020. So people were using it, but it was not as friendly interface like ChatGPT, where students could just do their homeworks and all of that. Right? It's still a model that does masked word prediction. If you give it a sentence, it will give you what will come in this mask. That was the role of this. But you could take the architecture, you could take the weights and tune it for your task, and you could get a good accuracy. So it was a good NLP model, but it was not a general purpose model. Yeah.
So let's say you do fine tuning on million words itself, would it be as similar as
So you're saying you ignore this first step and only do this. Yeah, that won't work at all because the network is too large and 1,000 examples are just too few. Billion examples of this nature, yeah, then it will still be a good model. Yeah, yeah. So people here, do you have questions? The one with the cap and to the left. Okay, so if you want to talk, please take it outside to the class. If you have questions, feel free to ask. So okay, so question, yeah.
It's like the data is billion tokens.
Yes.
So like in maybe vision or where we do like each data point is like different. Each image is like
Yeah.
25 ImageNet. So those many different and then batch processing we do.
Yeah.
So here is it a single stream? How do we do, or here also batches?
So here, when you're training, you will train in batches, multiple sentences together, like we do in, yeah. So just to look at some of the results of BERT, so they were very, very good at that point of time. Like, so you should compare this with the pre-OpenAI baselines, right? Pre-open, like you should compare this line, sorry, the first line with this one. So for some of these tasks, it was a huge jump. Like, so a lot of these numbers were very, very good, and a lot of people got very, very excited in 2018. And it was a really good model. There were lots of extensions like RawBata, DistilBERT, LBERT, IndicBERT, VisualBERT. There are like 1,000 different BERTs at this point of time, all pre-trained on, let's say, different corpus. So BioBERT is pre-trained on, let's say, biological related content. Medical BERT is pre-trained on PubMed articles and so on. Same architecture, but the pre-training corpus is different.
Here the pre-train itself is a different set of
Yeah. So the billion words, instead of coming from the internet, are coming from, let's say, medical articles. Only that articles, yes.
So it will focus it more towards some particular topic.
Say that again?
Fine tuning, then
Yeah, it will focus on that particular specific task, yes.
Would it not become like I take that pre-trained model and train it only to med thing, so that will become a med part.
Yes.
Will that happen or like
No, so basically people thought we can use the original idea of BERT, but train it on, let's say, PubMed articles that were publicly available.
only that set of data?
Only that set of data, yes.
then for the task, like we can use it for prediction of sentences. Like can Word do that? If we ask one question, can it?
No, BERT cannot answer questions. BERT cannot answer questions directly, like it cannot produce answers, it cannot produce poems. It can be used to, so I have not shown this here, but you can repurpose your BERT to predict some things. So like you can have explicit markers in your input whose representations you can use further to make predictions that, okay, this is the start of the answer if you are doing extractive QA. So if you know the answer is in this page and you want to know the span where the answer is, you can do that with some additions to BERT. But BERT directly is just a masked fill in the blank model. Questions, yeah? I'm not so aware, you should check that. Maybe there might be one, yeah. Question, yeah? Pre-trained models. These are pre-trained for, let's say, specific corpus. Oops. Yeah, they could have started with that, but some of them did not do that. 1 second. This is. Yeah, okay. Yeah, so these are all extensions pre-trained on new data.
So now I can just take the embeddings out and just do dot product and figure out where this line came from and all that. Would I even need to use BERT at that point? Just take the embeddings.
Yeah, you can do that. In fact, like Google search operated in that fashion in 2019. It will take embeddings from BERT after, let's say, layer 12 or layer 16 and try to match with document embeddings and surface and use that for retrieval. Yeah, exactly. You don't have, like, that is what Google did, for instance, at 2019. Yes. Okay. So so you can, instead of having an encoder, you can pre-train a decoder also. These are natural candidates for the language modeling task. The decoder is just like predicting next word, one word at a time. This is the strategy underlying GPTs, right? And so GPT is nothing but a giant transformer. It's called generative pre-trained transformer. So exactly the same architecture. It was released in June 2018. GPT-1 was called GPT, not GPT-1 obviously. 12 layers similar to the BERT, small parameters, similar hidden sizes, trained only on books. If you were to use GPT-1 for a task, what you had to do was you had to keep these special sequences like extract, like these extract, and corresponding output values of this will then be used to do, let's say, sentiment analysis. So even GPT was, even though it was a language model, it was still being used like BERT, where you would take a representation, take an embedding in the last layer and use that for a task. If you had two tasks, like if you had two sentences and you were computing similarity, you would attach two different models at the extracted output and then make the similarity prediction. So fine tuning was the only way to use GPT-1 for tasks other than language modeling, and you would have these tokens which you will use to then extract representations and then project them to the task of your choice. So I think GPT-2 was when things got interesting. So this is still, I think, like maybe a 4 to 6 author paper. So this is still a very, maybe within OpenAI, a nascent project. This is larger model with 1.5 billion parameters, no more million, billion. So 1500-ish million parameters, 1.5 billion. And the total number of layers here are 48. The hidden dimension is 1600. So this is just a scaled up version. But I think, and it was trained on millions of web articles, not just books, but web articles. So this is when they scaled GPT-1 to GPT-2, and it began to show zero or few shot learning capabilities. So this was like, I think, a very aha moment within OpenAI, where they realized that even simple things like, you say summarization, to do summarization, you take a long article, let's say that you want to summarize, put in that article, and after that just add TLDR. TLDR is too long, did not read, and the model will generate summaries. So it's a good language model that can generate summaries just by looking at TLDR, because it has seen a lot of web articles which maybe have this, so TLDR has some meaning. And they say that generated summaries only begin to approach the performance of classical neural baselines, just barely outperforming 3 random sentences from the article. So summarization, one good summarization baseline is just take the first 3 articles. Typically people will say the most important things in the start, and that's a good baseline. So this model was beginning to get better than those and beginning to approach the performance of classical models which were designed and trained for summarization. This is not trained for summarization, this is trained for language modeling. Similarly, if you give some examples of English sentence equal to French sentence, and then give an English sentence and put this equal to mark, it will start to generate some French output, which is again like kind of mind-boggling. Why would that happen? The results say that GPT-2 gets 5 blue score, which is slightly worse than a word-by-word substitution. So again, like translation is not as simple as word-to-word substitution. It is still a poor translator. But the fact that it can do translation is quite amazing, right? It was not trained to do translation. It was trained to do next word prediction. So they also say that on this test set, GPT-2 is able to leverage its very strong English model and perform significantly better, achieving an 11 blue score. 11 blue score is still like poor. You can barely make out what the person is saying, but this is again like non-trivial. It's a language model at the end of the day that is doing translation for you by just this few examples. And you might ask like why is this even happening? The paper also says that, what's going on here? The paper also says that the internet is full of these examples. So internet has these sentence like, I'm not the cleverest man in the world, but like they say in French, I'm not a fool, right? This is the French translation. So this naturally occurred on the internet. Similarly, like there are sometimes articles which say that this person on Twitter wrote this, which translates as this. I hate the word perfume, Burr says it's somewhat better in French. So these are like again examples on the internet which give you translation, right? I mean they tell you a little bit about translation.
These words, we will suppose this is now in bold. Does it somehow able to capture that bold?
No, this is made bold for emphasis. The model is just doing next word prediction. A generative pre-trained transformer is doing next word prediction.
And there are some letters in different languages. So the inputs with like a word in the language model, like
Yeah.
we input it. So do we input the ASCII character?
No, that is actually a whole different, like how you do it is called tokenization. Like one thing you can think of this is very simply like you can say I'm going to just split by space and this is a token, this is another token. But more sophisticated ways to do tokenization, there is an algorithm called byte pair encoding. There's a very nice lecture by Andre Karpathy on tokenization. If you're interested, I would encourage you to watch that. So this paper shows some zero-shot results of this 1.5 billion model. And they don't look bad at all, right? So they don't even fine-tune GPT-2 because zero-shot is looking like it is starting to get interesting. I feel this is when OpenAI realizes that there is a lot of room to scaling here. Few-shot performance is looking good. They want to scale this effort, but again, OpenAI being OpenAI, like they've always used hype to kind of like elevate their position, and they say things like due to concerns about large language models being used to generate deceptive, biased, abusive language, we are only releasing a smaller version. We are not releasing the dataset code or GPT-2 model weights. And the research community was very mad at this, like, oh, this is not very different from BERT, it's just a scaled up version, nothing really fancy, like, oh, come on, like people were angry. There are a lot of like shit takes on like this. You can read about them on Twitter or other places. Interestingly, people found that GPT-2 generations were quite credible. They gave a score of 6.9 on 10 on a scale of credibility. Interestingly, people were also unable to identify whether the output was from GPT-2 or human written. So humans are largely incapable of distinguishing, even though you could build a classifier that scores 95% on detecting GPT-2 versus human output. But one thing to remember is like this is a moment where I feel OpenAI realized there is value to scaling this up. So they take some more time and scale this. So this is not 1.5 billion, this is 2 orders magnitude higher. Than GPT-2, right? And this was 10x higher than anything that existed at that point of time. GPT-2 is trained without any gradient updates, just few shot, no fine tuning, nothing. And they very clearly say our basic pre-training approach, including model data training, is very similar to GPT-2, which is relatively straightforward scaling up of the model size, dataset size, and diversity and length of training. So just more data, bigger model. We use the same model, same architecture. And same problems, like humans can't identify GPT-3 output from human output. So if you look at the GPT-3 model, this is 175 billion. So the dimension, the D I was talking about, which used to be 64, has been scaled up to 12,288. The number of heads, which were 4 in smaller versions of BERT, are now 96. The number of layers are 96. So it's a massive scaled up version of a very simple architecture that was around in 2017. But again, like, this takes a lot of compute and like belief that this is the way forward, which is why I think OpenAI was quite distinct and unique. I think they realized very clearly in GPT-2 paper that there is value to this because of the few shot capabilities. Yeah. Not necessarily the same. Yeah. I mean, like the general intuition is let me train on more data, let me use a bigger GPU or more GPUs, and then you start to think what all can I increase. You can increase D, you can increase N, you can increase heads. So all of these things go up.
So how they said that it is used without any gradient update.
So it's just the pre-trained model that's used as a next word predictor.
But we are adding number of layers and heads into GPT-3.
This is all pre-trained. So these are not, so nothing is fine-tuned here. GPT-3 is a language model. If you want to do a movie review, like if you want to predict the sentiment of this, so let's say you want to use GPT-3 for sentiment analysis. Okay? So what would you do is you will say, here is my movie review. Write down that review and then say the sentiment is and blank. Now you have converted the task of sentiment analysis to a task of language modeling. So if the model says positive, the sentiment is positive. If the model says negative, the sentiment is negative. It could happen that the model says awesome. So you will have to do some mapping back to whether it's positive or negative. If you control the model, if you know the outputs, like if you have the values of probabilities, you can always compute what is the probability of P of the word positive in this context compared to probability of the word negative in this context. If the former is higher, then you say that this is positive sentiment. If the latter is higher, you say it's a negative sentiment.
We have a model and then we have a task, and for that task we have actually pre-tuned that model by providing this part, that whether it's a positive or negative.
So here you are just using lots and lots of articles on the internet to do the pre-training. The task that you are using that to just give examples. Like you give 5 examples and call this a 5-shot learning model. You gave 5 movie examples and said that the sentiment is positive. Another movie review, sentiment is negative. Another movie review, sentiment is positive. Now 4th one, you don't say what the sentiment is and you leave the sentiment as the model will say positive or negative.
But again, if we are increasing the layers,
Yeah.
then why we don't need to use the gradient descent? Like, is it
So
like each layer is trained and
so pre-training happens using gradient descent. So pre-training, like there is no magic to like there's no other magical way to pre-train a network. You are still using gradient based methods. So pre-training is done through gradients, but the point is after you have pre-trained, the model is fixed. You are not changing the weights of the model. Like in BERT, like in GPT-1, you were fine tuning, you were changing the model weight slightly to suit your domain or your task. You are not doing that now. So when you go to ChatGPT, you ask a question, the model weights don't change for you. Okay?
Here we are not doing any fine tuning.
We are not doing any fine tuning. Yeah.
How do we
How do we do the translation? How do we tailor it for your task? By giving some examples. Few shot learning, or it's also called in context learning. This is like you tell the model that you want to do 5 plus 8 equal to 13, 7 plus 2 equal to 9, 9 plus 8 equal to 17, and when you say 10 plus 3 equal to, the model will correctly say 13. Just because of these examples, the model has realized you want to do addition. So through these examples, you are telling the model what to do. Similarly, if you want to do spelling correction, same model, same weights, you just say misspelling, correct spelling, misspelling, correct spelling, misspelling, correct spelling. Now if you say, let's say break, it will give you break. Just one thing. Similarly, if you want to say English, thanks, French is merci, hello, bonjour. Similarly, you can convert this into an English to French translator just by giving some examples. Same model is doing addition, same model is doing translation. Just the difference is context. Yeah. So could happen, yes.
That can have same probability or like.
Yeah, depends. Like I don't know what the model will choose. I think very likely it will choose the first one that's more popular. Yeah.
After a point, you will realize that you cannot, do it even further. They get into fine tuning. So the question is, when you do fine tuning, is it the process is very similar to gradient in terms of how you do gradient descent?
Yeah.
Yeah.
Any different? Right. So great question. So in GPT-4.3 era, like let's say we have very big models. So the general advice is that if you can give examples and if you can give clear instructions, then the model might be able to do the task for you. If your instructions are clear and examples are clear. But if you feel that you don't exactly understand the task itself, it's very hard to give instructions. But you have 1,000 examples or 2,000 examples or 10,000 examples, then you can do fine tuning. In fact, OpenAI allows you to privately fine tune a model if you give them your data, and it will give you an endpoint that you can use to use a fine-tuned GPT. I mean that the objective is the same. It will take your input and say it will attach input colon, output colon, and it will do next word prediction on your data.
And then
Update the entire model for you. So there are some ways where it says I'm only going to update a small part of the network, like these are low rank adaptations and so on, like LoRa. But one idea could be like I'll update everything for you. I don't think they do that because then they'll have to store the entire model for you and host it for you. So they only update a small portion called an adapter. Only the adapters, yes.
how is this kind of relevant to this generative model?
So this is all like generative because it is generating the next word for you. So it's generative in that sense. Right. So last slide. So they are also starting to notice that like these few shot capabilities are more present in larger models. So if you go from one example to 10 examples, from 0 examples, the jump is huge here, whereas the gradient here is very, very low, right? So the gradients on these smaller models are very, very low, but gradients here are much bigger. So some people say that these capabilities are emerging from large models. So this is no prompt, as in you just show examples. Like you don't tell we are going to translate Hindi into English. You just show dhanyavad, thank you, just examples. Here it's instruction plus examples.
Then how do we compare it on the existing test data sets for different tasks, like maybe language translation as, because in that there just we have X, not Y, and Y is to be predicted or
Yes.
but in here we do some kind of instruction to the model.
Yeah.
So then that is conditioned on how well we can steer it.
Yes, yes.
So then those numbers,
Yeah.
like you were showing these were pre-OpenAI era based on classical models.
Yeah.
And these are based on some adaptation that you have to necessarily do so that it predicts for that. That does not then paints a good picture.
So basically, like let's say you only care about translation quality. Let's say we have like he has a model that's based on RNNs, she has a model that's based on transformers. Some person added a very elaborate prompt, gave thousands of instructions, lots of clues, lots of pampering, whatever, right? And this person has a very straightforward prompt, translate into English, and only 2 examples. From just an evaluator perspective, I don't care. All 4 of them are black boxes for me. I will just generate output on a new unseen samples and then look at what is the quality of outputs they are giving me. Again, it might be unfair to say that GPT performed poorly because maybe he might not have prompted it well enough. So that's why people make this joke a lot. Maybe you didn't ask it nicely, right? So there might be potentially some gap between what the model knows versus what you are able to coax from the model. So maybe the model knows the answer to your question, but your language is insufficient context.
These translation or like generalization capabilities are summation of the prompt and the model capability.
So it is summation of, yes, it is like a function of the best quality prompt and the model. Yeah. Yeah.
Do you feel that we are using tasks for which LLMs are a bit of an overkill, even for things like classification problems?
Uh-huh.
We have definitely trained TF-IDF,
Yeah.
traditional ML models to do that. But the fact that people are going towards it, do you feel that we can blindly trust that and use LLMs for everything?
Yeah, so great question. So like, should we use LLMs for simpler tasks which we know very well how to solve? Even translation for that matter. Okay. So some very simple tasks I feel need not use a large language model. There's like, it's like a big giant truck. Like if you want to just go 200 meters to buy, let's say, a packet of milk, you don't need to pull out your giant truck to do that, right? The cost of running this is high, energy footprint is high. Sometimes the model is very big. Either you make this very, very slim, very, very efficient, very, very cost effective, energy effective and use it, or rely on things you used to rely on in the past. Having said that, these models will also have capabilities or still are having capabilities to invoke existing tools and systems. So instead of predicting tokens, this model can also potentially be trained slightly differently to go to a calculator and make a calculation. So it can, like I can have the model produce a specific format like calc a comma b, which basically means, let's say, calculate the sum of a and b. And whenever I see that, it actually invokes a calculator, gives me that sum. If the generated output is correct, like if the parameters are correct, then I can 100% rely that my calculator is not going to hallucinate, right? So a lot of that is also happening right now, where LLMs are being used to tell what tools to run, what code to run, what system to search. This is called like tool use. If you're interested in this, there is a nice paper called Toolformer, like tool plus transformer, Toolformer. You can check that out. Yeah. So mathematically, like hallucination, these are probabilistic models at the end of the day. They assign probabilities to what can come next. So when you say PM Modi visited, like he goes everywhere, right? Like we don't know whether it's Switzerland or Mauritius or wherever. So there is a probabilistic interpretation to it, right? So you cannot necessarily interpret that as a fact. In some cases, if there is enough context and if the model has seen that, it may give you correct answers. So the only way I think to develop and like really trust these systems is to improve its accuracy to a point where you feel that it's going to give you correct answers very, very often.
Improve accuracy by using the model or basing the prompts?
Both. Using a better model, larger model, more data, running more stress tests, asking or like changing your prompt so that it's more clear, all of that. And so you need to do all of that to be able to ensure that the accuracy is good enough. These models are also great for tasks where generation is hard but verification is easy. Like you want to create, let's say, a big advertisement for your company because you are hiring candidates. You can very quickly read whether the hiring pitch is compelling enough, is correct enough, but you don't want to write those 500 words, right? So verification is much faster than generation. So those kind of situations, models are good. You are verifying, you are in the loop, you are verifying, but these models are doing the generation for you, which is I think what happens a little bit in the homework scenario also. Like people look at it and it seems like correct, and people submit it. Right? Yeah. Cool. So that's pretty much what I had to cover in this course. But there's a lot of content on the internet. The purpose of this course was not to really get every detail right and have everybody understand every bit of it. I think my personal goal was to lower the barrier of you learning about large language models. So I hope I've done some justice to that and you can maybe pick it up and know more about it through other sources. Thanks.